So everybody got this down? Awesome. Significant figures in scientific notation. We learned about both of these things on Tuesday. Now we're going to combine them and talk about how they function together. So when you are turning a number into scientific notation from standard notation, you're going to want to keep the same number of sig figs. Okay, so keep the same number of SF when going from standard to scientific notation. Oh, yeah. That means if you have a number like 1020.0, first of all, how many sig figs does this number have based on the rules that we learned on Tuesday? 5. Can anyone explain to me why there are 5 significant figures? Yeah, because it's a decimal. So we have 2 non-zeros, which always count. We have 1 zero between the non-zeros, which always count. And the trailing zeros are significant because there is a decimal present in that number. That means each one of these is significant. And so when we turn this into scientific notation, it will have to be 5 significant figures. Okay, so I'm going to write 1.0200 because that's all of my significant figures times 10 to the what? 3. So we count over 1, 2, 3. It's a big number. It's larger than 10, which means it's going to be a positive exponent. 1.0200 times 10 to the 3. We can go the other direction, a small number less than 1, 0.0690. How many sig figs does this number have? Great. Yeah, I heard 4, because there is a tendency to want this 0 behind the decimal to be significant. It doesn't matter where it is in relation to the decimal. It matters that it is a leading 0, that it's in front of the non-zero numbers. That means it does not count. Leading zeros to the left of non-zero numbers never count. The 0 on the right counts because there is a decimal in that number. So we have 3 sig figs, which means our scientific notation will need 3 sig figs. 6.90 times 10 to the what? -2. Because it is a number less than 1, you're going to have a negative exponent. You moved your decimal twice. 1, 2. That gives us -2. Questions so far? Okay. 10200. How many sig figs? 3. So in this number, we do not have a decimal, which means these 2 trailing zeros do not count. So we only have 3 significant figures. 1, 2, 3, which means that our number is going to be 1.02 times 10 to the 4th. Beautiful. And our last but not least example. How many sig figs? 1, which means it's just going to be 6 times 10 to the 1, because you moved your decimal 1s, well, your imaginary decimal, because we don't have a decimal, which means that this 0 is not significant. The only significant figure there is the 6. So we talked about scientific notation and the use of scientific notation to save space, especially when you're writing a scientific graph. When you're writing really big or really small numbers, there's one more use of scientific notation, and it has to do with significant figures. Does everybody have this down? Raise your hand if you need a little more time. Excellent. Sometimes we want a particular number of significant figures, but the number we have is kind of awkward to make that happen. And what I'm talking about in this case is 600 written with 2 significant figures. So if I write, if I write 600 as is, okay, there we go. If I write 600 as is with no decimal, how many significant figures do we have? 2 here. If I add a decimal here, which is an awkward, we don't generally see numbers like this, but you can put a decimal there to make those 0 significant. But how many significant figures do we have now? 3. So neither of these is correct. We want 600 written with 2 significant figures. We want it specific to the tens place. You can write it in scientific notation, 6.0 times 10 to the 2, problem solved. Questions on that? So that's the third, the second or third use of scientific notation. Saving space, labeling graphs, and giving the correct number of significant figures when you have an awkward number of zeros for that number of significant figures. Okay. Let's talk about rounding significant figures. In the past, I haven't made this rule. I'm going to make this rule this semester. Always round up from 5 in my class. I know some of you learned it differently. In my class, always round up from 5. It makes my grading job easier. It makes the job easier for the people who grade the papers for me as well. So, always round up from 5. Which is what I was always taught. So when I heard that people sometimes round up from 5 and sometimes don't, I was a little confused. But round up from 5 in my class. So rounding is really important when it comes to changing the number of significant figures you have in a particular number. So if I wanted to write 19246 with 4 significant figures, how many does it have right now? 5. So I want to end the significant figures in the tens place. This is when we round up and we place a placeholder 0 in the ones place, okay? So a common mistake, I say cut off significant figures and people just truncate the number. You want it to be the same value, you just want it to be less specific. You want a different number of significant figures. So it's gonna turn out like this, because you round up to 5 from 4, 6, and you have 5, 0 there. So now you have a number that has 4 significant figures, but it's the same value, yeah.
But we don't round 5 now?
No, because I want just 4 significant figures. If, for example, I was rounding, if I wanted to write this with 3 significant figures, I still wouldn't round up, because rounding up, you wouldn't round up from 4, right? It's always the number right after the one that where you're cutting it off. Excellent question. And then similarly, if I wanted to write 263 with 2 sig figs, here, all I do is take that 3 away and add a 0, because I just round down to 260, no decimal point. So do not just truncate the numbers there. You have to remember to put that placeholder 0. If it's a number less than 1, it's a little bit different. For example, if I have 0.02093 and I want to write that with 3 sig figs, in this case, I can just cut off that last sig fig, right? So here we have 1, 2, 3, 4 sig figs, because once again, those leading zeros do not count. Zeros to the left never count. So here we're just going to cut off that 3, and we're going to write it as 0.0209. 0.8965 with 3 sig figs. Here you're going to round up, but you can cut off that last sig fig once again. So remember, we round up from 5. So I'm just going to round this up to 0.897, leave off the last significant figure. An awkward 7. And my final example here is writing 0.8965 with 2 significant figures. In this case, we're going to round up from 6, but we're at a 9, so we're going to have to turn this into 0.90. So in this case, we do have to keep that extra 0 to make sure we have 2 significant figures. So this is how I want you to round significant figures in this class. And most teachers, I know Catherine and John, who teach 110, 111, if you go on, they will want you to round like this. Any questions thus far? Yeah. Yeah, exactly. So yeah, you just consider, the 5 in this case doesn't really matter. You're just considering the fact that this is 5 or greater, so you're gonna wanna round this up from the 6. So in that case, you're gonna have to go 1 more, just as you would round 89.6 to 90, something like that.
I'm gonna ask you that too. The reason why you don't want to always think about dropping numbers off, because if you look at the 263, for example, if you just knock that 3 off, 26 is way different than 260, right? Right? Would you rather get paid $260 or $26?
Yeah.
So don't make sure not to drop numbers. That's what she's talking about.
Yeah, and it may seem like this is pretty simple to a lot of you. I see these mistakes all the time. That's why I'm going over it. Any other questions? Yeah.
Well, is there how many significant figures you want on the exam?
That depends. That's a very good question. Sometimes I will, but I'm actually going to start teaching you today how to figure out how many significant figures you should have. And that's actually a very good lead into the next section. So thank you for that. Significant figures in calculations. Yeah. So for example, on the first exam, I'll have a few questions. Each exam, I generally have the first page has to be short answer or multiple choice, and the rest of the exam, it's generally 4-ish pages, is longer questions, math questions, or conceptual questions. And so on the front page, I might say, turn this number into something with 3 significant figures or something like that. And then on the longer unit conversion questions, then you'll have to determine how many significant figures. There are 2 rules that have to do with significant figures in calculations. One has to do with multiplication and division, and the other has to do with addition and subtraction. Now, what do I mean by limiting? What limiting means is determines how many significant figures are in the answer, okay? And the least number of sig figs for multiplication and division, when you're using your numbers in your calculation, the one with the least number of significant figures will limit the significant figures of your answer. And in addition and subtraction, the least specific sig fig in the numbers that you use will limit the sig figs of your answer. Let me walk you through some examples of this. The first rule is more intuitive than the second rule. Don't forget that second rule though, because it's pretty important. So for the multiplication and division, we have 5.02 times 89.665 times 0.10. First number, how many sig figs? 3. Second number, how many sig figs? Third number, how many sig figs? Beautiful. So how many sig figs should our answer have? 2. The least number of sig figs is limiting. So our answer, which would be 45.0118, we're just going to keep these two significant figures, meaning our answer is 45. Likewise, 5.892 divided by 6.10 equals, well, first of all, which number limits our sig figs? 6.10, because it has how many? 3. So our answer, which if you kept more sig figs than you need, 96590, we only want to keep these 3, which means we're going to round up to 0.966. Questions so far?
They kind of like similar rules then.
Well, this is the same rule, right? Because because it's the, so I haven't gotten to the addition subtraction. That's when everything goes out the window. All right, everyone have this down? Great. Now for the addition subtraction rule. Remember, the least specific sig fig is limiting. That means the one that's in the largest digits place. And I'll give you an example to clarify that. 1,025 plus 300. 1,025 is specific to which place? I'm talking, so it starts at the 1,000, but its significant figures go all the way back down to the ones. Yeah, so we're looking for the smallest digit place. What is 300 specific to? The hundreds. So which is least specific? 300. Because we know that 1,025 is exactly 1,025. For example, if I had 1,025 people in my class, that's how many I would have on my roster. But if I say, oh, I have 300 without a decimal, that means I could have 320, I could have 297. It's about 300, right? So the further your further your significant figures go to the right, the more specific it is. But the least specific number limits your answer. which means that our answer can only be specific to the 100s place. Our answer would normally be 1325 if you were doing this just, you know, normal addition. However, we have to stop those significant figures at the hundreds place and add placeholder zeros to 1300. The reason for this is, if I said I had 1,020, exactly 1,025 people in one class, and I had about 300 in my other class, total, I couldn't say that I have exactly 1,325 students because I said about 300, which means that when you add those two numbers together, something that's about 300 and exactly 1025, you can only say that you have about 1,300 students. Everybody get that? Excellent. Yeah. So think about if you have a liter of water and you just kind of, you know, it's a beaker and the only notation you have on it is liter. You don't know if it's 0.995 liters. You know it's about 1 liter. If you add like one tiny little drop of water, right? Even if you know the exact amount of that tiny little drop of water, it's still going to be about 1 liter because you don't know, you can't say it's 1.0001 liters, right? Because you started with about 1 liter. So it's all about knowing precisely knowing how much you have. Exactly, because in my class, in one class, I don't know precisely that I have 300 students, even if I know I have 1,025 in the other class. It's about, you know, in one class, you know, it's about this much. In this class, you know exactly. When you add them together, you only know about the number you have.
In the textbook, actually, if you actually did buy it, there's a good section on it which talks about like accuracy versus precision, which is what this is. So that does explain really specifically why it happens like this.
You can also look up the difference. I don't really talk about the difference between accuracy and precision in my class, but you can look that up online and know the difference. But precision is how specifically, like, you know the answer, to what place you know the answer. Okay. So let's do an addition, a subtraction version. Oh, sorry, I just want to talk about this. Notice that even though you start out with one number that has 4 significant figures and one number that has 1 significant figure, you end up with an answer with 2 significant figures. So you have to do the math here to really know how many significant figures you will have. If I have 1.0 minus 0.32, which is our least specific number? 1, beautiful, because it's specific to the tenths place. And 0.32 is specific to the hundredths place. So our answer will be specific to the what place? Tenths, beautiful. Our answer, so just normally if we did the math without thinking about significant figures, we would get an answer that was 0.68. We have to round that though to 0.7 because our answer can only be specific to the tenths place. So we have 1 significant figure in our answer.
Is it important to always put 0.07 or could you just put 0.7?
Like 0.7?
Yes, sorry.
I don't care if you put the 0 in front of the decimal as long as you make it very clear that you have a decimal. Yeah, because some people can write decimals and it's like famous. So just make sure you put in those decimals and make sure I can see them. Make sure they're
Why is it to the tens place? Is it because of the 1 or
the 0, right? So point something is the tenths place, not to be confused with the tens place. And so, and then 0.0 something is the hundredths place. So it's like 1/10, 100, 1,000, and so on. I want to do one more example of the addition and subtraction rule. 2.80 plus 7.8 plus 1.369. To what place should we limit our answer? Tenths. Not the hundredths or the thousandths, because we are 7.8 is specific to the tenths place. Which means that our answer, which we have 11.969, what are we gonna have to round that to? 12.0. Because we want to cut it off, we want to cut off the 6 here, but we have a 6 right there, which means we're gonna have to round up 11.9 to 12.0. Do not forget to keep that 0 because that is, we want to be significant to the tenths place. So we have 3 sig figs. Questions? Let's do some practice. So when I ask you to practice problems, you are welcome to work together. You're welcome to ask me, or welcome to ask Katie. So let's do 1, 2, 40. And Jose, when he's here, he'll pretty much only be here on Tuesdays. Katie's here both days.
And don't worry, you will have a lot of practice with this concept. It's not just one day.
Yeah. Yeah, we'll be doing a worksheet on that's going to involve all of this, everything we do on Monday.
It'll be on your exam review.
It'll be on the exam review, all of that.
I have worked on it.
Yeah.
So come see me.
Alrighty, and here we go over this. Okay. Can anyone remind me of the rule for addition and subtraction? Least specific digit. Yes, the least specific sig-fig. Which is what? 240 because it is specific to the tens place, while 28 is specific to the ones place. Let's do the math. So it would be 268, right? However, you have to cut it off at the tens place, but you need to make sure that it's the same approximate value. So we would round it up to 270 with that last zero being insignificant. Any questions on that? Any clarification? All right. And a lot of people I saw got that. Now, what's the rule for multiplication and division? Least number of significant figures. So how many significant figures does 1,000 have? One. Why? Trailing zeros only count if there's a decimal. There is no decimal. So there is one non-zero in this number. It is the only significant figure. 320 has how many significant figures? 2, because once again, that same rule. Trailing zeros are only significant if there is a decimal. Once again, there is no decimal. So out of the 1 and the 2 significant figures, 1 is the least number. Your answer, it would be 320,000. We have to round that down to 300,000. You can also write this as yeah. Any questions on that? Okay, I see. Okay, hold on. Yes, right there. The answer is 300,000. Because, oh, sorry, because I was going to write it in scientific notation. 3 times 10 to the 5th is another way to write this. Once again, one significant figure, but just in scientific notation. Yeah, sorry. I was in the middle of writing something. Any other questions? I rounded it, so the answer, right, if you just, and I always recommend just doing the math for that step and then figuring out the significant figures, right? So 1,000 times 320 is 320 pounds, right? However, I can only have one significant figure. I have two is 320 pounds. So I have to replace that two with an insignificant zero. So it has to stay the same number. The least number of significant figures limits the answer's significant figures.
And it helps you to identify that. What I personally do in my experience is, since I don't only need one sig fig, I draw a line under the first number.
Yeah, that's a really good idea. So if you come in and you say, well, with the 268, I only want two figures, that's where I need to stop my significant figures. You can do that with the 320,000 and be like, well, what do I do with that two? Round it down to a zero. The last answer would, let's see, is 9 point, can anyone tell me what the actual answer is? 9.84? Okay. However, I'm really bad at doing math in my head in front of 100 people. So always double check the math I do in my head. So it is negative, yes. There's another perfect example. And I put a negative there, but it's not registering. There we go. Flagging. Okay. What do we have to limit this answer to? Tens place, because this 12.8 is specific to the tenths place. 2.96 is specific to the hundredths place. 12.8 is least specific. We have to cut this off at the tenths place. So our answer is negative 9.8. Questions, concerns? Okay, now we're going to combine these rules. Never forget, guys, never forget your PEMDAS. Your order of operations. You'd be surprised how many mistakes are made just based on this one, forgetting this one thing. PEMDAS, use it every day. The thing about using both addition and subtraction and multiplication division rules in calculations is you have to reevaluate the significant figures after each step. You can't just throw it all in your calculator, pick the least number of significant figures in the whole problem, and then just count that as your significant figures. It really depends on what you do first, what your numbers are. So let's go through and start with an example. 3.489 times 5.67 minus 2.3. According to PEMDAS, what do we do first? Yay, okay. So parentheses has addition and subtraction. So you have to use the addition and subtraction rule, which is the least specific. What is the least specific out of 5.67 and 2.3? Beautiful. So our answer will, for that part, will be specific to the tens place. Awesome. So if we just do the math there, I'm going to leave the 3.489 times 3.37. Now, you might be wondering why I'm keeping that 7 there. And the reason is it can change your answer later if you just completely cut off those significant figures if you just wrote 3.4 there. What I like to do is keep that extra significant figure, but just mark keep that extra digit, but just mark which figures are significant, so that in the next step, I know how many significant figures I have. Now, in 3.489, how many significant figures do we have? 4. And in our other number, how many do we have? 2, because I marked those. Our answer has to have 2. Our answer would be 11.76, but we round it up to 12 because we can only have 2 significant figures. So does everyone see why I stopped, reevaluated my significant figures, and then did the 3.489? We can do another one. Let's do the same one without the parentheses. Now, the reason I'm having you do the same thing without the parentheses is because not only will your answer change, your number of significant figures will change based on your order of operations. So in this case, what do we do first? Yep, and that gives us a 19.79, but how many sig figs can we have there? 3, because in multiplication, it is the least number of significant figures. 5.67 has 3 significant figures. Our answer for that part alone is 3 sig figs. Once again, I marked that I have 3 sig figs, but I keep that 9 around, just in case. And then I 2.3. Now, what's special in this case? What are they both specific to? The tenths. So our answer should be specific to the tenths, which gives us 17.49, which we round to 17.5 to have it specific to the tenths. Not only did our answer change from 12 to 17.5, our number of significant figures changed from 2 to 3. This is why you cannot just put this in a calculator and evaluate based on the least number of significant figures. You have to go through, use your significant figures on each step to figure out how many you will have at the end, because it will change, once again, based on your order of operations. Questions? Yeah, sorry.
How come I actually from 3 figs to 2 because it's 2.3?
It's because, so here, so you're asking why this last step? Yeah. We ended up, so here, 19.79 has 3 segments based on the multiplication, okay? And I marked that we have 3 segments. That is specific, if we're only talking about our significant figures, that's specific to the tenths place. 2.3 is also significant to the tenths place. So it doesn't have to do with the fact that 2.3 has 2 significant figures. It's that both numbers are specific to the tenths place. So our answer has to be specific to the tenths place.
If it weren't to be like that, would you go with the new numbers?
Yeah, for example, if I subtracted 2 and just like 2,
Yeah.
then your answer would only have 1. Then your answer would be specific to the ones. Okay. Yeah. That's a good question. So she asked, well, what if that 2.3 was specific to a different place? For example, if I instead of 2.3 just had 2. We're specific now to the ones place, which means this would be not 17.5, it would be, or it would be 17. Well, it would be 18. 18, yeah. Because, sorry, I was trying to erase. Okay, because if 19.79 minus 2 is 17.5, 0.79. We want that specific to the ones place now, which would mean it would be 18. So depending on that second number, the second step can always change the significant figures from the first step. Oh, someday. Okay. Works out the same though. Okay. All right, so I hear a lot of muttering. Let's do some practice problems and see if it clears up those mutters. And if not, just we'll talk more about it, okay? We are going to start conversions today. Yeah, because we're not doing a worksheet. Sorry, was that you? Or?
Yeah, that's me.
Okay, sorry, I thought it was. Oh, okay. Please do these two. Yeah, that's actually my next page. Oh, okay. And I have to. Sorry, I'm going to rewrite the second one so I have more room to answer these. And don't forget PEMDAS, please. Sometimes Okay, so can everyone listen in, please? Thank you. So in number 1, okay, I just said please listen in. Okay. In number 1, what do we do first? Divide 24.7 by 89. So I'm going to bring down the 16.8, and my answer to the 24.7 divided by 89 is 0.278. But how many sig figs should that answer have? 2, because 24.7 has 3 sig figs, 89 has 2. With division, it's the least number of sig figs. So only the tenths and the hundredths place are significant. Keep that extra sig fig around because it might change your answer if you round it up now. Sometimes it doesn't, but sometimes it really does. So now we're going to subtract. And what's the least specific number here? 16.8, because it's specific to the tenths place. 0.278 is specific to the hundredths place. So we're going to limit our answer to the tenths place. That gives us 16.5. And I saw a lot of people get that right. So any questions on this one? Was that a hand back there? Okay. Okay, first, and then I'll get the hand. Yeah. Yeah. The amount of sig figs of, can everyone please listen up? So she just said, does the amount of sig figs in 0.278 become irrelevant? Not necessarily. I mean, if it had, do you mean like the number overall? Yeah, so the number overall, like for the 0.278, that has 2 sig figs. We're having 2 sig figs, but it doesn't matter that it has 2 or 3. It just matters that it's more specific than the 0.8. I had another question here. Oh, sorry.
Wait, I'm confused about why it's not 7. Because those have 2 sig figs.
Because you're thinking about the multiplication division. Right, so now we have moved past multiplication division. We are now in addition subtraction. With addition subtraction, it's the least specific. So 16.8 is specific to the tenth. So even though our answer we got from the last part has 2 significant figures, it's more specific. So we have to limit it based on the 16.8. Any other questions? Yes.
So do you discard the sig fig that you got before and then start?
You discard the sig fig rule you got before. However, the sig fig that you got before can affect what you had before, what the new step. So, for example, if instead of having 16.8, I have 16.849, in that case, the 2 sig figs that I brought down from before would affect, because that makes it specific to the hundredths place with the B less specific than 60.849.
On tests, if you do end up rounding and use that with short my work, you say that
If you round in the first step,
Yeah.
I would give you credit. But yeah, I would say, so the answer that I would give the graders would be the one that has the rounded. That would be a case of, they would probably be able to identify that it was a rounded answer. However, sometimes they might miss that. So in that case, if it was marked wrong, you would just come say to me, I rounded the number earlier, I should get these points, and I would fix it for you. All right, I'm going to do the number 2. We do the multiplication first. So 240 comes down, and we add to that 169.4. However, from 169.4, how many of these figures are significant? 3, because 6.25 has 3 significant figures. Actually, so does 27.1. So they both limit the number of significant figures. So when we get our answer, it would be 409.4, but we have to be specific to the what place? Tens. This 0 is insignificant because there's no decimal. So this is specific to the ones place, yes, but this is specific to the tens place. So our answer is specific to the tens place, which means we round up to 410.
Could you change the 1 to 5.1?
Well, in that case, you would round it down to 169 because it's 3 figures, right? Yeah, you could. In this case, it would change the answer. Yeah. Because I'm not rounding up from the 4, I'm rounding up from the 9. See that? Because I want it specific to the tens place. And so specific to the 10th place, 409.4 is closer to 410 than 400. All right, let's move on. We're going to have more practice on this. Don't worry. Let's move on to dimensional analysis. Can everyone get out, if you have the unit prefix sheet, get that out. I will bring more on Monday. I forgot them today, but I will bring more on Monday for those of you who didn't get them. I'm going to run out of time. I wanted to get all the way to cubing. Can anyone tell me what from Tuesday, what the prefixes you need to remember are? Kilo? Centimeter. What's next? Millith. Micro. Nano. If I say μg, you need to know that's micrograms. If I say nm, you need to know that's nanometers. I will not tell you what that is on the test. I will say, I cannot answer that. Yeah. How much is a kilo? In relation to the base weight? 1,000 or 10 to the third? What is centi? 10 to the negative 2. Milla? 10 to the negative 3. Micro? And nano. I always tend to get micro and nano mixed up. I just remember that nano means 9, nano 9, 2 n's, right? It's important that you understand these in terms of conversions. And what I mean by that is that a kilo is 10 to the third. So a kilogram is 10 to the third grams. But 1 gram is equal to 1/1000th of a kilogram, so 10 to the minus 3, and I'll write that out. So 1 kilogram equals 1,000 grams, or 10 to the 3. 1 gram is 1 fraction of a kilo, so you need to figure out which is bigger, right? A kilo is bigger. 1 gram is 1/1000th of a kilo. So 0.001 kilograms equals 1 gram. Okay? Both of these statements are true. And you need to be able to identify that a kilo is 1,000 because it's bigger, grams are smaller. So 1 gram is 1 fraction of a kilo. In the same vein, I always remember centi because how many cents are in a dollar? 100. Sometimes I get some crazy answers for that. So 1 meter is 100 centimeters. This is the most common way you say. We won't use centiliters. That's not really something that we use in this class. But a centimeter, you should know what a centimeter is. It's not that big. And so if 1 meter is 100 centimeters, how much of a meter is a centimeter? 0.01 or 1/100th, right? So we're doing the inverse, okay? So 0.01 meter is 1 centimeter. Bunch of centimeters in a meter. 1 centimeter is a fraction of a meter. Does everybody see that? Okay, so in the case of micro and nano, when you get a millimicro and nano, when you get smaller, so, I said nana, it should be nano. Your grandmother is 10 to the minus 9th. Okay, so 1 meter is 10 to the 9th nanometers, okay, because 1 nanometer is 10 to the minus 9th meters. Okay, that means that 1 meter has 1 billion nanometers. So 1 nanometer is 10 to the minus 9th. It's 1 billionth of a meter. You have to know these because we will be using these in the conversion. Questions thus far? Awesome. We will use them right away. Sorry, do you need me to go back? Yep. Okay. There we go. No. Billions.
I know. Like, right.
Okay. If I say, we're going to just start with 1-step conversions. How many grams in 2.7 kilograms? This semester, before I ask you to start any math problem, or at least most math problems, I'm going to ask you, should this answer be big or small? Why should it be big? A gram is smaller than a kilogram. So a number of kilograms should have a lot of grams in it. Do that every single question on your test, because if you make a calculator mistake and you just write down your answer and you don't think about how whether it makes sense, you will get those points wrong, okay? Now that we know that this should be a big number, let's start out with 2.7 kilograms. So when we're doing unit conversions, our goal is to get rid of whatever we started with and end up with what we want. So I'm getting rid of kilograms and I want to turn that into grams. That means that I'm going to put 1 kilogram on the bottom, right? Because in any multiplication and division, if you put a 2 on the top and a 2 on the bottom, they will cancel each other out. That's what we're doing. We're putting kilograms on the top, kilograms on the bottom. They're going to cancel each other out. 1 kilogram is equal to how many grams? 1,000. And look, your kilograms cancel out and you're left with grams on the top. That's exactly what you want. So your answer will be 2,700. Now let's talk about significant figures in this answer. Oh, sorry, that should be just grams. We start out with 2 significant figures. Now, you might say, well, 1,000 has 1 significant figure, so does 1. Well, placeholder ones like that 1 kilogram don't count towards your significant figures. Neither do conversions within a system. So if you're going from a metric to a metric, as we are doing here, grams are metric, kilograms are metric, that is an exact number. So even though we don't write it that way, that number, you can imagine, has infinite significant figures. It's 1,000.0000000 per 1.0000000, right? So when you're converting within a system, metric to metric or English to English, that conversion factor does not affect your sig figs. That means that we want to end up with 2.7 sig figs. Sorry, 2 sevens, 2 sig figs, because 2.7 has 2 sig figs. And this is a multiplication and division problem, which means it's just the least number of sig figs. Okay, so 2,700 grams is accurate in terms of sig figs and in terms of our answer. And that's a big number. That's what we wanted in the beginning. So I could say, how many meters in 7.89 micrometers? Sorry. Big or small answer? Why? Meters are much, much, much larger than a micrometer. So if you have 7.89 micrometers, you shouldn't have very many meters in that. You should have a very, very, very small amount of meters. Your exponent should be negative when you put it into scientific notation. There are 2 ways you can write this. I'm going to start with the way that I prefer. And that's when we start out with 7.89 micrometers. I always like to keep things in terms of positive exponents. So what I do is I put 1 meter on the top. 1 meter is how many micrometers? 10 to the 6. Okay, so notice that I don't have 10 to the minus 6 there. I have 10 to the 6 because micrometers are really small. There's a million of those in 1 meter. So when you do your math, it's going to be 7.89 divided by 10 to the 6. And that's going to give you 7.89 times 10 to the minus 6 meters. Guess what? That is a very small number. Do we have the right number of sig figs? Yes. Because this is a metric to metric conversion, we imagine that has infinite sig figs. That's an exact conversion. So we're going to base our sig figs on the 7.89. The other way you can do this is 7.89 micrometers, And then you're gonna put 1 micrometer equals 10 to the minus 6 meters. It's gonna give you the same answer. You choose the way you do this, and you be consistent, and you know what you're doing, okay? So for me, it makes more sense to sometimes have the bigger number on the bottom, as long as I always keep that positive exponent. For some people, it's gonna always make sense to just have the number on the top and just put 10 to the minus 6 or 10 to the third on the top always. But you have to know that in this case, the reason that these two say the same thing is because, just like I was saying earlier, 1 meter has 1 million micrometers. 1 micrometer is a millionth of a meter.
And so that we will always suggest, here is not as important because it only has 1 step, but before you put any numbers, put your units first. That way you actually put them in the right location and they cancel.
Yeah.
You're gonna see many times where they'll flip it, and they'll put meters on the top, or on the bottom, I mean, sorry, and then micrometers never cancel out, like micrometers square or meters is not right. So always write your units first and then build your numbers.
And at the end, just double check that all of your units cancel out. Okay, let's do a longer conversion. Multi-step conversion. Big or small answer? Big. Nanometers are super small. Kilometers are like just over half a mile. So you're gonna have a lot of nanometers in a kilometer. What's really helpful in this case, this is not going to be a one-step conversion because we don't know, not off the top of our heads, the conversion between nanometers to kilometers. But you do know kilometers to meters and meters to nanometers because we have our unit conversion sheets. Our unit prefix sheets. Now, I'm going to write a unit map. So I'm going to go from kilometers to meters to nanometers. Which means I'm going to start out with 6.21 kilometers. I'm going to put a kilometer on the bottom. 1 kilometer is 1,000 meters. 1 meter is 10 to the 9th nanometer, which means my answer is going to be 6.21 times 10 to the 12th nanometers. Which is a very, very big number, which is what we figured out we should have. Question? So in this case, what I did was I put my kilometers, I crossed out my kilometers. I crossed out my meters. So even the in-between unit should cancel out. So I go from kilometers to meters. I cross out kilometers, then I want to cross out meters. I end up with nanometers on the top. That's great. There's one more example I want to do, and that is when you go between systems. So how many inches in 5 points? This is just going to be a one-step conversion, but conversions between systems, between metric and English, because the metric and the English systems were developed independently, they do not have exact conversions between them. So it's not exactly 2.54 centimeters per inch, it's about 2.54 centimeters per inch. Which means that those sig figs are going to affect your answer. I'm going to start out with 5.692 centimeters. And I'm going to put Once again, I want centimeters on the bottom, inches on the top, because I'm getting rid of centimeters and I want to go to inches. I have about 2.54 centimeters per one. That's a placeholder 1 inch. So how many significant figures should our answer have? 3, because the 2.54 in this case affects your significant figures. So if you divide 5.692 by 2.54, you get 2.24 inches, 3 significant figures. We got rid of those centimeters. We ended up with inches. Thank you. Have a great evening. And definitely, if you have questions, come on up.